Okay, I'm going to continue to do this over and over until I get it right. Hi everyone, my name's Nate. This is the first video in a series of videos I'm going to be doing that is going to cover both ideas, concepts, and also problems, examples that should go alongside the first 2 semesters of your undergraduate electromagnetics course. Electromagnetism, preference. Now, a couple assumptions are being made going into this, that you've already taken Calculus 1, 2, and 3, wrong, and that you're either in or you've already completed your introductory physics courses 2. I can't imagine it being taught in 1, but no, I could be mistaken. Anyway, in this subject, we're concerned with charges, how charges interact with one another, how they affect one another. Now, we're going to take a charge to just be a physical property that matter can possess. Things don't necessarily have to have a charge. That's kind of boring, especially from where we're coming from. We're concerned with those particles, substances that do have charge. We're concerned with how they affect one another. Now, we all know going into this, if you have similar charges, like charges, they're going to repel. Opposite charges are going to attract. That act of either attraction or repulsion, that's what we're concerned with. When you say that you have 2 charges and they either pull or push, it implies that there's a force that's doing the pushing or the pulling. That force is what we're concerned with. Now, important thing to note going into this, we're going to be concerned with charges that are staying still. But at least for the time being. We don't want to consider charges that are moving. When you start doing that, things get a lot more complicated. You have to consider, are they moving at a constant velocity? Are they accelerating? If they're moving at a constant velocity, then they start generating magnetic fields. We don't want to consider that. For the sake of this being, the charges that we're considering for the time being are going to be stationary. Coulomb's law, just to be explicit, might as well write it out. Alright. Now, Coulomb's law pretty much states what I just said. If you have 2 charges, or even more, there's going to exist a force between them. Now, more specifically, that force is directly proportional to the product of the 2 charges themselves, and also inversely proportional to the square of the distance between the 2 charges. Now, this is actually pretty much identical to the way the gravitational force is written. In your introductory course, you should have been shown the gravitational force can be written as F sub g is directly proportional to the first mass times the second mass divided by the distance between the 2 masses. Pretty much similar form for the electrical force. Thing to note, when I say electrical force, I'm considering the force that's between the 2 charges that are stationary. Of course, when you start considering moving charge, you have magnetic force. For the sake of this, when I say the electric force, I'm considering the force acting on 2 stationary charges. So our Q1, Q2, over the square of the distance between the 2 charges. Now, the same way your F sub g is actually equal to G m1, m2 over r squared, where g is your proportionality constant. More specifically, the gravitational constant in this case. Your electrical force has its own proportionality constant that's usually written as K. Actually, I haven't seen it as anything else, so let's roll with K. Equal to K, Q1, Q2 over r squared. Now, your K value is a proportionality constant. It has a value. That value being K is equal to 8.99. Most people write 9. I like to be explicit, so I'm writing 8.99. Times 10 to the 9th meters per farad. Okay, this is nice. Yeah, nice. Thing is, while this is true, K is also equal to something else. Actually, let me just write it down real quick, and then we'll talk about it. K is equal to 1 over 4 pi epsilon 9, where in this case pi is still your 3.14159, etc. Your epsilon naught is a constant. It's a new constant. We're going to call it the permittivity of free space, in which it holds the value 8.85 times 10 to the negative 12th farads per meter. I always want to get these mixed up, flip them, things happen, and terrible things happen. Anyway, with this being said, we can rewrite our electrical force, substituting this in. F sub E is equal to Q1, Q2, product of the two, over 4 pi epsilon naught R12 squared. Whoa, Nate, what are you doing? This new notation. Okay. Just a little bit of explanation of this guy here before I go any further. In the systems that we're considering, we're not just concerned with 2 charges. We can be concerned with 3, 4, 5, however many you want to consider. As such, we have to consider the distance from the first charge to the second, also the first to the third, and the second to the third. And they're not always the same distance. And so you get a lot of R's that are being thrown back and forth. Things get a little bit confusing. So, for instance, suppose we have 3 charges, where this is Q3, Q1, and Q2. Now, these charges have some distance between them. And they're not always necessarily the same distance. So if we were wanting to talk about the force Q1 has on Q2, we would use the value R12, which would correspond accordingly. If we wanted to consider Q2 to Q3, instead we would write R23. Simple enough. Likewise, as you guessed it, R13 for charge Q1 to Q3. So that's Coulomb's law. Or at least the basic form of it. In the next video, I'm going to go over Coulomb's law in a little bit more in-depth vector form. Pretty sure the time's running pretty high on this video. Anyway, hope you guys enjoyed. First video in doing this. Hope to pump out a lot more, and I look forward to seeing you in the next video.